So what I've covered so far is how to deform the category of modules. And the category, we started with the, let me just write a few things. Oh, yeah, okay. So what I want to describe now is a thing called the tensor factor. This is sometimes called a fiber factor. The first thing, so let me just clear up a bit of confusion about Casimir operators and R matrices. So let's start off with D, L plus, L minus, right? Where here this D is the double of the Lie bialgebra L plus equals L, and L minus equals L dual. Okay, so remember I constructed this double thing which contains L and L dual, and I just use the notation coming from Manning triples to describe that. Now, there are two things which I want to look at. One is R, which is the sum over sum of Li plus tensor Li minus. Where Li runs through a basis for the L plus, and Li minus runs through the dual basis, and omega is R plus TR. Okay, that's just mean R symmetrized. So there was this little sort of frisson about whether omega was symmetric or not. And I think what I was doing was confusing the R, which is the R matrix, with the Casimir element, which is the R matrix symmetrized. Anyway, through this data, so we've chosen an associator. Phi, and you fine. This is in what did I call it? T3, and all right. And what omega allows us to do is to find theta, a thing called theta, from T3H into Hom M V1 tensor V2 and remember here that this M, this category M, is what I call the Drinfeld category. So its objects are representations of D, and the morphisms from V to W are power series in morphisms over D to V into W. So this is defined using omega. So this gives the I'm just summarizing, associativity constraint phi V1, V2, V3 is theta of omega, and we have the commutativity constraint beta V1, V2 from V1 tensor V2.
I'm sorry, P is defined using omega or associator?
I'm sorry, thank you. omega defines theta, right? Omega defines theta, and the associativity constraint is theta applied to the universal thing. And this thing is beta is S composed to e to the h omega over 2, where S is just a straight transposition. And then the summary, these tensor products here are all taken in M, so they're all taken in the category M we're working in the Drinfeld category. So there's the associativity constraint, there's the commutativity constraint, and the theorem is that, in fact, with this associativity constraint and this commutativity constraint, the category M becomes a symmetric monoidal category, a braided monoidal category.
Sorry, I have a very silly question, which I should have asked this morning. You take the category representation of the Lie algebra you've been saying all the time, with their usual tensor product to begin with.
Yeah.
But these also are bialgebras, we have emphasized.
Yes.
So the co-bracket also defines a slightly different tensor product.
Okay.
So
Now,
which
wait.
one are you talking about?
I'm talking about, right, the co-bracket on L is used in making the Lie bracket on D. Right? It's used to make the Lie bracket on the double. And that's the Lie bracket I'm talking about. L has for the moment disappeared out of the game. Okay?
And how does this relate to...
Right. So my constructions from now on go with a man in triple, right?
As you said.
Right. A Lie algebra, two subalgebras with satisfying certain properties. Of course, the co-bracket is being used up in constructing that man in triple.
So is there a relation between representations of L as a bialgebra and D as a Lie algebra? If you don't have an immediate answer, you can ignore.
I don't have an immediate answer, but you can think of the answer, right? Because you've got to give a representation of L, a representation of L dual, and some compatibility on them given by the cocycle. So there is an answer, but I'm not working in that category. Okay, I'm working now with this Lie algebra. Okay, so we've got a braided monoidal category now. Now. We're going to study the functor. So A here will be the category of topologically free K, which is power series here. Okay, and we're going to study the forgetful functor F from M. Well, forgetful, I'm not sure if that's the right word. That's certainly the phrase Etingof and Kazhdan use. But it's given in various ways. It's given like this. F of V is Hom M U of D into V. Okay? So this is nothing more, of course, than V of H. There's nothing more than V of H, because such a homomorphism is uniquely determined by the unit goes, and the unit has to go to a power series in H. The power series elements B and H. But it's writing it like that, writing it in this way, gives us a way of manipulating with this functor. Right? So in other words, you can say exactly the same thing by doing some tricks with the representations, but somehow it's easier to say, or easier, I'm not sure, but somehow it seems easier to say in terms of the this form of it. Now, the first thing we could do is use the Verma modules. And these are just the modules M plus, which is going to be, so, and again, I'm interchanging between representations of the Lie algebra and representations of the enveloping algebra all the time, but forgive me for that. M plus is going to be the universal enveloping algebra of L, D, what's my notation? Yeah, D, L plus, L minus. Tensor over the universal enveloping algebra L plus with 1. One being a trivial one-dimensional representation. If you think in terms of representations of the Lie algebra acts by 0. if you think of representations of the universal enveloping algebra, the universal enveloping algebra acts by its augmentation into 1. Right? M minus is U of D tensor UL minus Y. So these are the so-called Verma modules. The basic property they have is this, that let's see. Let's see. Right, sorry, I'll be from the next one again. Yeah. So by the Poincaré-Birkhoff-Witt theorem, the multiplication map maps the universal enveloping algebra of L plus tensor the universal enveloping algebra of L minus into U of D. Right. I include this universal enveloping algebra into the universal enveloping algebra of D. I include this into the universal enveloping algebra of D, this into the universal enveloping algebra of D, and multiply in the universal enveloping algebra of D. Right. This thing is a linear isomorphism. Right. Remember, D, amongst other things, is the direct sum of those two subalgebras. And from this it follows several things follow from this. M plus is free rank 1 over U of L minus, right? And I write B plus for the basis element. B plus for the basis element. M minus is free rank 1 over U of L plus. And the basis element of that, I put B minus. That's the first thing which follows. But these modules have look like that there. So what we get is an isomorphism of modules from the universal enveloping algebra to M plus tensor N minus, and that's the kind of decomposition which I'm going to use all the time. So we get maps of UL modules first one is UL and this map is given by 1, the unit in there goes to B plus tensor B minus. B plus is the basis element in M plus, and B minus is the one in M minus. So this thing is called phi, and phi is an isomorphism of UL modules. So the first thing we've done is split the obvious representation of UL on itself into a tensor product of two representations.
Okay. N is equal to N plus. What is N? D. N plus, right?
L is D.
What's
no,
M?
D. L is D.
Ah, you said maps of UL modules.
No, it's D.
UD modules. Ah, thank you. What? Thank you. Thank you. The other thing we have from this is maps which are called I plus and I minus from M minus into M minus tensor M minus. And these are given by B plus goes to B plus tensor B plus. And this one is given by B minus maps to B minus tensor B minus. And you see, it's important here that, of course, that if I take u u of L plus acting on B plus is is 0, as is u of B minus, u of L minus acting on B minus, and that makes these two things well-defined maps of that produces a well-defined map from M plus to that. I think. Look, here's my notation.
Yes, okay.
Right. Okay. Okay. I mean,
I'm sorry.
yeah. So in other words, the fact that this thing tells you that the map from the universal enveloping algebra, D, which sends one to that thing, factors over the tensor product over L minus, over L plus. Sorry. Okay, so it follows then that our FV this forgetful functor, as Etingof Kazhdan called it, is co-represented by. Sorry, I lost my page. It follows that FV is therefore HOM in the category, in the Grothendieck category, M plus tensor M minus into V. Now, of course, now you see, to do these things correctly, well, M plus and M minus are both infinite dimensional, right? They're isomorphic to polynomial algebras linearly, and I see I'm going to get into trouble now, right? Because typically I'm going to move this M plus over there and put a HOM in it, and so on and so on and so on and so on. So I'm going to do one or two unnatural things, right? Which, if I did properly, using the topological things from the start, would be completely natural, right? But it's easier to think of this.
So F index V is F of V.
F of V, sorry. Now, I need to tell you now what I mean by a tensor structure. So, well, let's just suppose we've got some C. Well, I'll just do it for the functor F. It's obvious. I'll just do it for the functor F. It's obvious that what I'm doing has got a general definition, but I'm not going to give the general thing. So so I've got this functor F from M into A. M is the Grothendieck category. A is the category of topological free K of H modules. So a tensor. It's a collection of functorial isomorphisms J, B, W from F of V tensor F of W into B tensor W. It's F of B tensor W. So not only are we assuming we're playing the same game again, right? I mean, you'd normally assume that the functor preserves the tensor product, but no, I'm not saying it preserves the tensor product. I'm saying what I got is a collection of isomorphisms from the tensor product. Now, these things have to satisfy an obvious condition. They have to satisfy satisfying the associativity identity, which I'll write out. F Oops. Right. Right, so far so good. So far, so good. I've written down the obvious thing. But now I have to put.
the W on the left hand side. It's VW, FV, FW, and FU.
Oh God, sorry.
Just
Thank you.
that's my job.
It should be my job actually. frankly. And now you see. So far, I've used nothing about the tensor product, but now I put in the isomorphism given by the associator. Right? In there is the twisting. I'm not going to write out that in any other shape or form. So, in fact, once again, the associator and the Casimir operator are going to define for us this tensor structure, and here it is. So define JVW. So this is going from let's see, JVW going from f of v tensor f of w into f of v tensor w as follows. Okay, so I start with V in Hom M M plus tensor M minus, and W in Hom M plus tensor M minus W. And I'll write it like this, right? So over here I put V tensor W. Right? Now this I map in, from this I map in M plus tensor M minus. Right? By V tensor W. And now, now I've got to rearrange the brackets. Okay? I've got to rearrange the brackets so I have an associativity isomorphism. So I write it like this. There's an associativity isomorphism here. Yes. It's the associativity constraint on those three. So that would be called phi 1, 2, 3. Now I've got to put in a commutativity constraint. Right, now I can turn them round. So that's a sort of associativity. Commutativity, well, associative constraint, commutative constraint And now I do the inverse. Now I unwrap that one. Right? And finally, I apply the maps I plus tensor I minus from M plus tensor M minus into that thing. Right? So that's so of course it has to be proved, and I'm not going to do this, but it has to be shown that this is a tensor structure. So the proposition is this. Now, so I read the proof in Etingof Kazhdan of this, and I must admit, it really threw me. Right? The proof is trivial, they said, because any braided monoidal category by MacLean is isomorphic to a strict one. So all you have to do is to prove these formulas for a strict monoidal category, they say. And they're easy, right? They're just straightforward things. And I mean, really, somehow or other, this seemed to me to be cheating, really, because the art is put in that associate to make things complicated, but the proof is take away the associate and make things simple. Somehow that doesn't seem to be fair, right? Certainly, whenever I try that for myself, it goes wrong. but it is, and eventually you get your head around it and you realize it does work. In A? No, because that's because well, I mean, yes, I am hiding it, but it is there, but it's the canonical one. There's no twisting of it. Absolutely correct. Absolutely. Okay, so now I've got a tensor. Now we've got the tensor. Now we've got this tensor functor. We've got these compatible system of isomorphisms between these things. And now out of this, I'm going to construct the quantization. I'm now going to construct the Hopf algebra. And remember D, I'm still working in the context where my Lie algebra D is the double of a Lie bialgebra. So what we do is set H to be endomorphisms of F. The endomorphisms of this functor F. Right? So, i.e., an element is an eta V from F of V satisfying naturality conditions. Right, so I give myself the endomorphisms of the functor. I literally mean the natural transformations from the functor to itself. It's an algebra under composition. And actually, what algebra is it? In fact, there is a canonical isomorphism theta from U D, the universe enveloping algebra D with H adjoined into H. So as an algebra, I've done nothing. I mean, again, this is all, again, when you think about this is all weird and wonderful, really, because so far I've done nothing, right? I mean, I've just said the same thing 3 or 4 different times. What's the isomorphism? Theta of x at v. So here, well, I finish. It's going from f of v into f of v. Is just given by is the action of x on the that's what it's given by. I just, after all, this thing, whatever else this thing v of h is, it is a module over the universal enveloping algebra. D is a module. V is a D module. So this thing is a module over U of dh, and the action. So that's the action of x on f of v. Yeah. Yeah.
I'm used to Tanaka duality for compact Lie groups. So I don't know how well it works for the algebras, but you don't ask your elements H to respect the associator and the gradient in some sense?
No.
You put the naturality conditions, but
Yes.
they're only for most routine representations.
Yes, only natural transformation of factors. I'm not going to say anything else. What I'm going to do is use the associator. You see, that's all I need in order to recover the algebra structure. Right? But I need to put on this thing a co-product and a co-unit and an antipode. And that's where the associators are going to come in. Okay.
Because in the group case, you only get an isomorphism. You ask extra conditions. Anyway, never mind.
No.
And the other thing that, the question that comes to my head when I compare the two, you don't ask L to be of compact type or something? Or
How do you mean?
It's finite dimensional.
that it integrates to, that is the Lie algebra for compact Lie group?
No. I mean, I want finite dimensionality in what I'm doing, right? Because really, I mean, that's a bad thing, and I should really not assume finite dimensionality. And then I have all these topological constraints come in. But I'm assuming finite dimension of the Lie algebra I start, the Lie bialgebra I started with, right? I'm over Q, so I don't like you asking me questions about integrating. I know what you're doing. I know what you're doing, and they are all sensible questions. I just don't have a clean answer. But don't stop asking, by the way.
Well, it's hardly a question. You have accused yourself of not having done anything, and it's true that everything is so functorial there. So the question is on the top blackboard, on the top right blackboard. Yeah, no, I mean the only thing we've done is to split this U of D into m plus tensor m minus.
Yeah.
So for instance, on the top blackboard, you could, instead of writing m plus tensor m minus, write U of D all over the place, and then just use the natural co-product to produce an arrow, which would do the same thing. So the only thing we've done is intertwine m plus and m minus, which I mean, where we've used the fact that we actually split U of D into m plus tensor m minus. Otherwise, you just write U of D, you use the co-product, and that produces.
Yeah, but I'm using the fact that it's been
No, I know, but I mean, can you just comment on this intertwining? I mean,
I'm not sure. You see,
here,
whether this thing with all its twisting is the co-product.
No, I know it shouldn't be.
It shouldn't.
Otherwise, it would be. I mean, wasted.
Sorry,
we wouldn't have done anything at all.
But right.
So
That's right.
this.
Yes. So you're saying that the classical case, I would just use the standard co-product.
If we hadn't split,
If you hadn't split,
in
that's
that
correct.
way, we
Yeah.
just, and then that would be wasted. So I would
Somehow you can see that the part in L and the part in L star are as being some kind of conjugate variable. And what you're doing here is kind of normal ordering.
Yeah.
If you're used to quantum mechanics, that's what is going on.
You're putting all the plus variables on one side,
Yeah.
and all the minus variables on the
yeah,
other
yeah,
side.
that's really the only thing we've done.
Yeah.
Shifting a minus tensor and plus tensor and minus.
Yeah, but I mean, we put in some pretty high octane fuel, right? Right.
Yeah.
The associator, we put in the associator. So I agree, but
And that's the difference with the co-product.
yeah.
On D.
In this right, that's going to come in the tensor product,
Yeah.
in the co-product. Sorry.
Mm.
Okay, so there's the algebra. Now, how am I going to do? Okay, here we go. Co-multiplication. I think I'm going to stick to the typesetters version. The complication. No, I can't do it. Co-multiplication. Right, so first of all, introduce F2 from M tends to M cross N into A by F2 of VW is F of V tensor F of W. So, of course, the endomorphisms of this F2 is just H tensor H. Right? The endomorphisms of that is just going to be the tensor product. And I'm going to define the co-product at that level. Now, define delta. Okay, so delta of A, right? That's something which is going to have to do something on V and W. And first I'll write the formula, and this is something I'm going to apply to V tensor W. This will be JVW inverse A V tensor W J. So I'll write it out as a composite. So it's just this thing, FV tensor FW. I've got an isomorphism with that with F of V tensor W. I should have just written it straight away like this. I've got an isomorphism with that with V tensor W. Now put A A in particular gives me an isomorphism that with that. And now untwist it. Well, now do JVW. So that's an endomorphism of the bifunctor F2. Therefore, this is an element. So this gives the co-product. Delta from H into H tensor H. Okay, so that again is kind of, I mean, it's just sort of functorial construction. I've got to go, so that's the co-product. So next I give the co-unit. So I've got A and H. Okay, A and H. Then consider A1 from F of 1 into F of 1. Now, what's 1 here? One is the is k, the scalars, with the trivial action of the Lie algebra, or the action of the enveloping algebra defined by the augmentation of the enveloping algebra. Right. So it's just it's just that thing. It's the unit for the monoidal structure, which is why I call it 1. Right. And I should have said that. Well, I'm automatically assuming that f of 1, this is equal to k of h. But this thing is, of course, uniquely determined by what the unit goes to. So that gives me an element of k of h. So this is uniquely determined by A1 of 1, which I'll of course call A1. I'll call tautologically A1. It's uniquely determined by what the unit goes to. And this thing is an element in k of h. So this defines the co-unit from h into k. That defines the co-unit. And finally, I'm going to give the antipode. This is fun. This is fun. I like because again, you realize yet again that I ought to have been honest and done these things with topological modules, topological vector spaces, and so on, because I'm going to take dual of dual of dual of dual. So the antipode. So given V in M, then I've also got V star, which is, I mean, by this Hom over K, V into K. That's another thing in M. It's another representation. That's another representation. Now, right? Remember. So notice that if I take Hom over M of V into M, that's not a representation. It's not allowed. Right? That thing's not an object in the category M. Objects of the category M. Well, I should have said finite dimensional representation, shouldn't I? Right? And again, you see, my sloppiness over the infinite dimensional thing. Right? So I've also got the canonical pairing sigma V from V tensor V dual into 1. Now this is a map of representation, a map of representations. In particular, it's an element of Hom M. But what I mean by that map is the map from V tensor V dual into the scalars, right? Where you evaluate this on that. So the answer evaluating one of those on one of those is not a power series; it's a number. That's all I'm saying. And now we get a canonical pairing. F of V. Okay, and again, you see, you think you know what I'm going to write down. I'm just going to apply F to this thing, but of course I'm going to twist it. So this is given by F of V tensor F of V dual. Well, that is by J V dual F of V tensor V dual. And now I apply F of sigma. So I use the tensor structure to get me into this. So I use some exotic isomorphism there to get me there, and then apply the standard pairing. Now, So this gives us an isomorphism. This pairing f of v dual to f of v dual. So the duals are in different categories there, right? All I'm doing is saying that power series in V star is power series in V star. Stupid, but the point is the twist which has come from there. Now, I call this xi of V. Oh, xi of V. Now, so we now go through a couple of steps. For any A in H, define, well, S twiddle A V to be f of V dual into f of V dual, and this is xi of V dual, right? Okay, and then I say this is right. Then I apply A is the element. A is in H. A is in H, so in particular it gives me a natural map from this thing to that thing, what its dual does. Right? And finally, I unpack it, so sorry, xi, I think, xi V star inverse. So this thing, right, that's the next thing we have. And finally I say, this maps f of V contained in f of V dual into f of V so there's something to check there, that this construction actually sends the natural copy of f of V in its double dual into the copy of f of V in its double dual. And C, define S V of A to be S V of A tilde restricted to f of V. And then you see that this family of operators is a natural transformation from the functor f of V to f of V. And that's the antipode. Okay? So they're all kind of tautological constructions. Right? I mean, there is a game of playing with fiber factors, isn't there? I do happen to know that. I think this is all part of a standard terminology. I think, for example, much of it's in Etingof and Schiffman, I think. Anyway, theorem, and this is not difficult. This is not difficult, again, because, well, you can use the principle that I can assume that as long as I'm checking with morphisms, as long as I'm not checking anything with elements, right? I'm never evaluated on an element. As long as I don't do that, I can just pretend I'm working in a strictly monoidal category. The theorem tells me that the algebra H equipped with delta co-unit eta and s is a Hopf algebra. So this really is a Hopf algebra. Okay, now. Now, of course, morally, well, I mean, as I say, these are straightforward things to check once you get your head. Now, morally, this has to be a quantization of the universal enveloping algebra of D. Why? Because what would have happened if I simply applied this construction applied this construction to D without, with M, where I place M by the category where the morphisms are maps of D modules. Of course, you would recover the standard Hopf algebra structure on the universal enveloping algebra D. Everything would work. You would recover the standard Hopf algebra structure. So morally, if you put H equals 0, you must get, if you mod out by H, put H equals 0, you must get the universal enveloping algebra. But actually, when you think about it, that's that's the kind of argument you can get away with for about 5 or 10 minutes, and then you have to say, well, what does that really mean? And you have to do something. And there is something to prove when you think about it. You can't, or at least I can't, convince myself, in all honesty, that argument I just said is more than morally correct. It's probably I should say immorally correct. Right? So you've got to do something to prove that it's a quantization. You don't have to do anything to prove it's a Hopf algebra. You do have to do something to prove it's a quantization of what you wanted. And this is where life starts to get difficult. This is where you have to do some fairly serious, again, it's really surprising. Once you have the courage to, once I had the courage to actually just take these papers of Etingof and Kazhdan at face value, right, and not think they were mysterious, complicated objects, you can see what to do, right? I mean, you don't have much choice, actually, which is why I think there are very few sort of slicked up or altered expositions of this in the literature. When you get to understand it, there's effectively only one way through.
You're saying there's really work involved? Because these constructions are exactly the standard analyticality, and this curly M is a retract of the all the representations. Everything is.
I mean,
natural. If you say I would have believed your moral.
Would you?
Actually, immoral correction.
Oh, thank you. I can stop that.
Well, maybe I'm naive.
You're equally naive.
Are you going to show us what happens to order 1? I mean, the coefficients of H.
That's right. That's exactly what you have to do. That's exactly what I was going to do.
Not order 0, but order 1.
A mod H squared.
Yeah, mod H squared.
Yeah. That's what I'm going to do. So first of all,
I was only talking about 0.
Yeah,
that's all.
That's all. 1 is more interesting.
well, sort of. I mean, it's a. So let's start off with delta 0 from U of D the usual coproduct. And then I'll write J0 from F of V. Let me get this right. It's how shall I write this? Yeah, right. This J0 of VW is the composite. U of D unperturbed so that's the undeformed. That's just the undeformed product of undeformed coproduct, sorry. Now what we do is let J in U of D tensor 2 right, so J is phi inverse tensor phi inverse of one tensor phi 2, 3, 4. Let's see, how am I doing on brackets, right? S e to the h omega over 2. Now I'm going to put the string backwards. 1 tensor phi 2, 3, 4 inverse. Right. So there's a monstrous formula. What on earth does this formula mean? Well, again, I'll write it down. I'll write it down in terms of morphisms here. It's this thing m plus tensor m plus. And then, first of all, I have to reassociate that. Then I have to do another associator. Let's see what yes, I have to reassociate in a slightly different way. Sorry, wait a minute. Excuse me. Just something. No. This one. Right, now I switch. Right, so I've done that, then that. Right. Now I switch. Right. And now I unpackage in exactly the same way. Right. So I'll just do two things and tell you what the end is. So that's the first lot. That's the first lot. Here's the switch. Here's the switch. Right? And then I do the inverse of what I did first time round. Right? Well, what? And I end up in m plus tensor m minus. And finally, to this, I can apply V tensor W. Right. So I apply that, and up here, I've got my B plus tensor B minus tensor B minus. So all I'm doing is applying something to B plus tensor B minus, but I'm keeping very careful track of the order in which you put things. And they're all the same arguments. They're all the same arguments. But we get a conclusion from this, believe it or not. Well, okay, I'm not. Well, there's a similar kind of thing for the antipode, and let me tell you what the conclusion is, which is what you wanted, Pierre, which is what you wanted me to say. So conclusions. e to the h omega over 2 is 1 plus h omega over 2 mod h squared. Phi is equal to 1 mod h squared. And j equals 1 plus hr over 2 mod h squared. Okay. So at least you see the first order terms of these things. Right? Theorem. Right? You have. Well, I haven't really done it carefully enough for the antipode, but I've done it for some things. Conclusion: the Hopf algebra H mod HH is a quantization, is isomorphic, sorry, to D as Lie bialgebras. Well, I've really left out. I mean, all I'm saying is there's some computations you can do, and those are the formulas you end up with.
U of t.
Are you sure then, because I don't see any bialgebra structure on H mod H.
Is U mod
Yeah.
right? Is U mod?
Hopf algebra.
Yes, sorry, it's Hopf algebras. Right. I have to say one other thing, which I'm just going. I'm not going to write out. But of course, I also want to know, as I said, if you have a quantization of a Hopf algebra, if you have a quantization of a universal enveloping algebra, that gives you a Lie bialgebra structure on that Lie algebra, right? So what Lie bialgebra structure is it? Well, it is the Lie bialgebra structure you get on D, right? Because if you choose one pair, mu and gamma dual, to make the Lie algebra structure, the Lie bialgebra structure will be given by gamma dual mu, right? So what is the induced Lie algebra, Lie bialgebra structure on D is the canonical one you'd expect. I'm still not. So that's the quantization. That's the quantization, and it's a certain amount of formal stuff. I still think. I'd love to believe you that my immoral argument is accurate, but I cannot convince myself that it is. But you have to do something now to get the fact that it is a quantization of what you want. Well, so now at this stage I've quantized D, but that's not what I wanted to do. I wanted to quantize L, right? D was the double Lie algebra. So what I wanted to do was really quantize L. But now, that's not, well, again, I'll tell you what the answer is, but again, I won't do enough calculations to, well, I mean, again, a certain amount of it is completely formal. You see, so what I'm going to do now is to quantization. Right. So U of DH, the standard notation. That's in my own notation. That's that algebra H. That's the algebra H I've constructed up there. From now on, I'll use the notation which is standard, really, right? UDH for that Hopf algebra H, the Hopf algebra of endomorphisms of the fiber of the tensor functor. Right. So remember that H is the endomorphisms of F, which is the endomorphisms of M plus tensor M plus, M minus. And what we define UH of L minus, L plus, sorry. So that's just a definition of the vector space UH of L plus. Right? Now what I do is I so embed A to U D of H as follows. So if I've got x, which is in, let's see, x in hom m, m plus tensor m minus into m minus, then I form I of x is 1 tensor x composed phi composed I plus tensor 1. So, right, okay, that's it. So it's given like this, m plus tensor m minus into m plus tensor m plus tensor m minus. Remember, that's what this I plus does. It goes from m plus into m plus tensor m plus. Now I've got to reassociate so there's where the associator comes in. And to this, I can apply x to get me to m plus tensor m minus. Right? Again, it's another one of these silly things you write down. And now you come up with the following rather nice formula. And again, the following nice formula. I of x composed I of y is equal to I of z, where z is, well, I won't. Okay, so there's a formula to check. Again, this is a formal thing, that this composite is just I of z, where z is that thing, right? And that tells you, you see, that in fact, hence, this thing, UH of L plus, is a subalgebra right? Because it's a subspace, and the product of any two still lies in that subspace. That's a subalgebra. In fact, then I'm going to basically give in here. So the Etingof-Kazhdan theorem is that, in fact,
Sorry, we can't read the last line. Perfect.
So again, the theorem is this. UH of L plus and UH of L minus are sub I'm not going to go. Again, this is all formulas. Right? And these things, UH of L plus. Remember, I started with I remember D. I started with the L D is the double, L plus is L, L minus is L dual. So I've ended up quantizing L plus. So, that's pretty much the end of the story, except I think I'm up to about page 17 of Etingof-Kazhdan, and they go on for another, they go on for 42 pages. And I can tell you the reason for that. That is because there's all this business about quasi-triangular Hopf algebras, the quantum double of Hopf algebras. There's a whole sort of paraphernalia of extra conditions you would want to do with quasi-triangular Hopf algebras, so on, so on, so on. I mean, I think they're very beautiful, but I'm not so concerned with those because, after all, what we wanted to do was to get some results about quantizing Lie bialgebras to feed in to the proof of Konsevich theorem. So there's a lot of interesting stuff to go, right? And that's what the rest of the paper is about. But I'm not going to cover that. Another part of the paper is where they actually become honest, because I think actually, having read the second part 2 of the paper, I don't think you'd have a clue what it was about unless you'd read part 1 of the paper. Right? In part 1 of the paper, they just do things. They do things exactly in the way I've said it is. In part 2, they adapt the method so they deal with the general case where you have infinite dimensional Lie algebras, and therefore you have to take the topology seriously. But I would never have understood that. Perhaps I still don't. But I wouldn't have had a clue what was going on unless they'd written part 1 first, which is this. Okay. Now the final thing they do is, they prove a theorem which says this. There is a functor from LBA over K into quantized universal enveloping algebras over K, right? Lie bialgebras over K, quantum universal enveloping algebras over K, so that L goes to, well, I'll just call this UH of L as constructed in part 2, because it's really in part 2 where they do it properly. There's a funny thing happens, actually, and I hadn't quite appreciated the significance of it until I thought about it. Was they say they do some calculation, and they point out that everything in this calculation is a universal formula involving the Lie bracket, the co-bracket, and functions of those. But in this calculation, they get 2 extra terms which occur. They're not of that form, but they cancel in the calculation. Right? So although the answer is a universal formula involving the bracket and the co-bracket and functions of those things, getting there is not. Right? Right? So they correct that by doing everything properly in the calculus topological vector spaces. But it's a funny fact. This is not really, this as it's described there is not really functorial. But there's a different way of describing it that makes it functorial. That's the first thing. Second thing is part 2 of Etingof-Kazhdan, when they say that everything here is given by universal everything is given by universal formulas. And once things are given by universal formulas, it's obviously functorial. Now, that is a statement about props. I mean, maybe do you know what the statement about props is? I couldn't get my head around the exact statement it was about props.
I don't know the statement just now, but I know where to find it.
Okay.
It's in the
Okay.
paper
Okay.
By Etingof and Enriquez. They
They do it. Yeah. Okay. So this has got something to do with props. I wanted to make. Basically, I finished. So, yep.
Were you going to finish this sentence or?
No.
Isn't it finished? Are you complaining about my lack of full stops?
The verb is not.
So that on objects, L goes to this, where UH of L is constructed in, is what I've been whittling on about all day so far. Okay. Sorry.
What you can say about this functor? Is it equivalence of categories?
I expected you to say something about this front.
Yeah, well, told you what it is on objects. I've muttered some words about props.
Because you also
which
say functor in this way, yeah?
Yeah. I think it is. No, yes, no. I mean,
I mean, like you've chosen E to start with. I mean, you've chosen a rational associator.
yeah.
So that function depends on phi.
Yes.
Yeah. So, yeah, I completely agree. F.
So for instance, I
But
mean,
that still doesn't mean that.
you could, no, I mean, you could,
So all of them could be natural isomorphisms.
so for instance, you have a natural action on the Grothendieck-Teichmüller group on these functors. So,
What?
so you have as
I
many,
don't.
as many
mean,
quantizations as
I
you
see-
have associators. Like.
I mean, I understand exactly what you're saying, but I have no reason, no honest reason to say that they all are different. And I mean, what you'd like, they are.
No,
No, they are.
why wouldn't that be an equivalence of categories? Maybe you can have Grothendieck-Teichmüller acting like that, but I don't see why it would contradict the fact that it's an equivalence of categories.
No,
For one algebra, you have many quantizations.
No, there is no. I mean,
but
you have a different equivalence of category if you take a different phi. But
Yeah,
this is an
because you have
equivalence of
What
category.
categories?
This is an equivalence of category as soon as on the left hand side for LBA, you choose as coefficient ring K double bracket H.
Yeah. What you're worried about, all you're saying is that there's more than one equivalence.
Oh, but they're equivalent. Yeah,
Yeah,
they're
yeah.
equivalent. Yeah.
Yeah, right. And in fact, the group of automorphisms, of course, of phi, acts on these equivalences.
Yeah.
I was wondering why.
I wanted to say one more thing. I wanted to kind of, just speculate from one thing. One thing which has surprised me is that after all, the problem Etingof Kazhdan solved is a deformation problem, right? Now this is feeding into the deformation of symplectic manifolds through some statement about two operads are isomorphic, right? And therefore it leads to the deformation of Poisson manifolds. Seems a very long route. Right, from one deformation problem formulated in precisely the same way as the deformation of Poisson manifolds is formulated. And I just wonder if, in fact, there's a route from this quantization to that quantization which doesn't involve going through operads. Bruno objects to me even formulating that thought.
Yeah, but why wouldn't we use a tool which is simple and allows us to govern all these algebraic things? We have a nice tool. Let's use it.
Yeah, but it's just you know what I'm saying, right? Somehow
Yes,
or other.
yes.
Somehow or other.
Nice.
And the other point I wanted to make is that we now have three proofs of the Deligne conjecture. In fact, right? Well, we have more than three proofs of the Deligne conjecture. Here's one of them, right? There's the McClure-Smith proof of the Deligne conjecture, right? There's the proof of the Deligne conjecture involving the compactification of the configuration space of k distinct points in the plane, right? What on earth is the relation between all these two things? Between these three things? I mean, are they fundamentally different, or are they just using the same thing in a slightly different way? I don't know, but it seems to me it's a good thing to analyze. What's going on here? What really is the relation between those? Anyway.
Just the proof of Deligne's conjecture from this point of view works only on the field of characteristic zero, and the one by McNary-Smith works over the integers. So in some sense, it seems
Good
to
point.
be quite different.
Yeah, good point. But anyway, I mean, my question still is, what on earth is the relation between all these things when you can compare them? Anyway, I'm done.